Hi, Calculus AB. So this is an introduction into Chapter 2, and it's called the derivative. And this is good news. We already have learned about it. And so the goal for the day is just vocab and language and how we can talk about the derivative in various ways. But you really do already understand the idea because it was covered in the last chapter. So the derivative is synonymous with a few different things. So that's what you'll see over here on the left side. It's synonymous with the slope of the tangent line to f of x at any point, or sometimes we say the slope of f of x at any point. We also use instantaneous rate of change at any point. We might also say derivative with respect to x. We might also use the verb differentiate, and that means to take the derivative. And I am going to highlight some parts of speech just to help you make distinctions between the things that we're going to do. So there are often times when a text might say differentiate this function, and it really just means to take the derivative, which is to find, the slope of the tangent line at any point. So the notation for the derivative is to use the apostrophe. And so we say f prime to indicate the derivative or the slope of the tangent line at a point, so at A. And this is a limit, and it's a limit that you already know. So the limit as h goes to 0, f of a plus h minus f of a all over h. There is another definition for the derivative, and we are going to focus more on that one in this chapter just because it's different than the one we did in chapter 1. And this is the limit as x goes to a. Notice that this is still a slope formula, and so that's why the idea that we had in the last chapter is still consistent. We are still talking about the slope between 2 points. In this limit, you're just bringing the 2 points really close together, whereas in this limit, you're bringing the distance between them close to 0. And so it really is the same idea that the 2 points are getting close together. The other thing that you might say is that f prime of x is equal to d dx of f of x, where this d dx is an operator, so it means to take the derivative of f of x. We might also say that f prime of x is equal to dy dx. And that just says, like, if your function is the same thing as y, this represents the slope of the tangent line. So just, again, to get into the language here of what's happening, I think that this is a value, and I think that this is a value, because you're talking at a particular x value of a. So this would finish a problem, and the answer could be like 2, or the answer could be like -1/3. In these two, your answer is going to be a function, and so you might have x's or other variables contained. You won't get a single value, but it will be a function in which you could plug in values to come up with a slope at any point. So here's a picture of a function, and I'm going to break this function down into a few different parts. I think that all of the slopes here would be positive slopes, and yes, they're changing, but we could say that f prime is greater than 0 because all of these slopes, these little tangent lines, if I were to draw them in, have positive slopes. Likewise for this region right here. Even the slopes here are changing, but all of them are going to be positive. And you could look in this group of slopes, and these slopes would all be negative. So you could say f prime of x is less than 0. So the derivative is less than 0. And up here and down here would be horizontal tangents, and those slopes are equal to 0. You can also talk about the derivatives and how they look like in life. Remember that it's like this instantaneous rate of change, and so you're really zooming in and coming up with a slope at a particular point. So it's kind of like a roller coaster, like here's the car in the roller coaster, or it could be like a surfboard against a wave. It could be like snowboarding or like skiing, sledding, etc. We're going to look at a couple examples. So number 1 is the definition that you guys have already seen in the last chapter. So use this definition to find the derivative of f at a equals 5. So this is a particular value. So the derivative at 5 is equal to the limit as h goes to 0, f of 5 plus h minus f of 5 all over h. And now you work through the algebra, knowing that this is your function that you're substituting in for. F of 5 is 24. Take a second, work through the algebra, and we'll come up with your value for the derivative at 5. So the derivative at 5 is equal to 10. In number 2, it says use the definition f prime of a equals the limit as x goes to a of f of x minus f of a all over x minus a to find the derivative of f equals root x plus 2 at a equals 3. So this is using the different definition of the derivative. And what's nice is they're telling us specifically which limit definition we need to use. So here we go. F prime of 3 is equal to the limit as x goes to 3 of f of x minus f of a, and so f of a will be root 5 all over x minus 3. The challenge with this problem is the square root. And so maybe in another class you learned how to get rid of square roots by multiplying by something convenient, and it's the conjugate. So where it's subtraction here, you're going to use the addition here, and you make sure that you multiply by the exact same thing in the denominator, because this is really just 1, and so it cancels out and it doesn't change the value of your first fraction. We're just going to be manipulating. Now when you multiply, I only recommend multiplying your numerators. Things in your denominator will end up canceling out anyway, and so you just have to worry about the numerator being nicer. All right, so for example, I was able to do the numerator pretty fast because your outside term and your inside term are going to go to 0. They're going to be exactly the same thing, and that's why this method works every time. So if you notice, your numerator is x minus 3, and so it will cancel out with this denominator. And now the limit can be found by just substituting in 3. So we'll have 1 over root 5 plus root 5. And because this is the AP course and the AP test doesn't mind if you leave things unsimplified, this is a fine answer. They do want you to be able to recognize other answers that are possible. So like 2 root 5 would be an answer, or root 5 over 10 would be equivalent answers. All right, number 3, find f prime if f is equal to 4 minus 6x. So now this is asking for a function, and because this function is a line, I know that the slope is always going to be negative 6. Likewise in number 4, y is a line, and therefore that instantaneous rate of change, the derivative, the slope of the tangent line, will always be 1/3. And the last question, remember that this d dx is a verb, it's an operator, it means differentiate, which means to take the derivative of. And they don't give us a limit definition, so we can choose which one we'd like to use. For me, I would prefer to use the h goes to 0 definition, and I save the x goes to a definition for the square roots. So I'm going to use the limit as h goes to 0, f of x plus h minus f of x all over h. And we don't have a number that we can plug in because we have to come up with a general formula for the derivative, such that if we had a point to plug in, we could find the value of the derivative at that point. So everything here is going to be just done in general x's. So x plus h gets input. Minus, throw in some parentheses here. It's the most common mistake that students make when they're doing this. Notice again that things are going to cancel out. So my x squareds are going to go away. My 5x's go away. And I've got a 2hx plus h squared plus 5h in my numerator. I can cancel out an h. And now I'm ready to substitute in my 0. So 2x plus 5 represents f prime of x. So look at that entire work that we just went through. It comes up with a general function for the derivative. So if I had said x is equal to 1, then I know that f prime of 1 is equal to 7. I'm just plugging it in over here. If x is equal to negative 3, I know f prime of negative 3 is equal to negative 1. So that's the nice thing about being able to come up with a general expression, and you use the exact same process that we used in the last chapter. All right, so we have homework problems, just a couple homework problems, and you'll find the link on Canvas. Bye.